One of the most interesting predictions in quantum mechanics is the de Broglie hypothesis, in which de Broglie suggested that classical particles like electrons, protons, neutrons, atoms, molecules, and even the matter particles that we see around us has a wave behavior associated with its motion. And he actually gave an expression to calculate the wavelength corresponding to this kind of a wave motion, which is known as the de Broglie hypothesis. According to this, the wavelength associated with the motion of a classical particle is actually equal to h upon p, where lambda is a wavelength, h is a Planck's constant, and p is the momentum of the particle. When de Broglie suggested this expression, he came up with this expression based on certain philosophical arguments about the grand symmetry in our universe. You see, light or radiation has dual nature. Light sometimes behaves like waves, but at other times behaves as particles. Light demonstrates this kind of a split personality between traditional waves and traditional particles depending upon which experiment we are performing. And de Broglie suggested that because light has dual nature, particles, the classical particles that we know, should also have dual nature. That means it should, apart from its particle nature, also have a wave nature associated with its motion, and he came up with this particular expression based on certain logical arguments, you can say, because at that point there was no experimental evidence to support it. But right after de Broglie gave his hypothesis, there were experiments that came up soon enough to prove that this in fact is actually a correct prediction. And one of those experiments is the Davisson and Germer experiment, where they demonstrated when electrons are scattered by some kind of a crystal structure, they experience diffraction. This is what today's video is going to be about. We are going to talk about the Davisson and Germer experiment, which experimentally provides a proof to a very bizarre prediction of quantum mechanics that particles behave like waves. Now, if you look at this particular expression, this expression contains a constant, which is the Planck's constant. And if you look at the value of the Planck's constant, the value of the Planck's constant h is 6.626 into 10 to the power minus 34 joule seconds, right? Which is a very, very small number. So if you want to calculate the wavelength associated with any kind of a particle, let's suppose I have a ball in my hand or a piece of chalk in my hand, and I want to calculate the wavelength. The value of the wavelength comes out to be very, very small because of the nature of the Planck's constant or the value of the Planck's constant. And because it is so small, we cannot really detect it in our day-to-day lives. In our day-to-day lives, all the matter particles that we see around us has a corresponding wavelength which is so small that we don't really have any detector or a measuring device to calculate that sort of a wavelength. So therefore, we have to go into the microscopic domain. We have to go in atomic dimensions. If we could go into atomic dimensions and look at particles like electrons or protons or neutrons or even atoms, and they are traveling at certain speeds, because their mass is so small and the momentum comes out to be so small, we can actually come up with situations in which the wavelength is of the order of the dimensions of a crystal material, let's suppose. So we can have situations in which the wavelength is of the order of a few nanometers or of the order of a few angstroms. If we can achieve that, then that wavelength can be detected by some kind of a system where the obstructions or the dimensions of that system is of the same order as the wavelength, right? So that is what this entire system is based upon. But before we talk about the Davisson and Germer experiment, let's first talk about another interesting experiment that happened much before that, which is the X-ray diffraction. You know, you must have all studied about what is known as the Bragg's law, right? When we talk about the Bragg's law, we are interested in X-ray diffraction. So let me give you a very small side note regarding that. So X-ray diffraction, or Bragg's diffraction. You see, diffraction is a typical wave behavior. You do not see classical particles or matter particles demonstrating any kind of a diffraction. Diffraction is inherently a wave behavior. So whenever we study the diffraction of X-rays through crystal structure, we see some very interesting results. Okay, that is what the Bragg's diffraction is all about. So essentially what happens is that whenever you have some sort of a crystal that has these various kinds of atomic planes, crystal planes, and you scatter some kind of an X-ray through it, and when you scatter some kind of an X-ray through it, then what you end up seeing is that in the scattered or the reflected radiation, you see certain kinds of maxima or peaks in that radiation. The intensity profile contains certain kinds of maxima or peaks corresponding to certain kinds of angles. And this can be very easily explained by the wave theory of light. You see, what happens is that if you have some sort of an incident X-ray, you can think of two distinct wavefronts that are getting scattered by two distinct planes of the crystal. Now, this is one of the simpler explanations of this particular phenomena. But what happens is that this top beam gets scattered by, let's suppose, the top layer of the crystal, and this lower beam gets scattered by the lower layer of the crystal. What happens is that initially the wavefront is in phase, right? But because of this nature of a scattering, the lower beam gets scattered by the lower plane. The lower beam develops a path difference compared to the top beam, right? So essentially, the lower beam travels an additional distance, right? This particular distance and this particular distance compared to the top beam. If we do the calculations, the additional distance that the lower beam travels compared to the top beam comes out to be 2d sine theta, where d is the interplanar spacing, theta is the angle at which the beam is incident compared to the surface of the crystal, and yeah, of course, the path length comes out to be 2d sine theta. And because of this particular path length, these two reflected beams therefore experience interference. Now, you understand what interference is probably, right? Yes, because when you have waves that are going together, their amplitudes can get added and create either constructive or destructive interference. So when two waves are traveling together, constructive interference simply means that the intensity profile is going to be higher, and destructive interference means that the intensity profile is going to be lower. Now, what Bragg's diffraction suggested, by the way, the Bragg's diffraction was an explanation that was provided by two scientists, Lawrence Bragg and I think William Henry Bragg. So William Henry Bragg was the father and Lawrence Bragg was the son, and they together provided an explanation for this kind of a X-ray diffraction pattern. And they said that because of this path difference, there is an interference pattern that gets created, and the constructive interference condition basically comes out to be n lambda is equal to 2d sine theta. So this is the formula for constructive interference. So whenever the scattered radiation satisfies this particular condition, we get a maxima in the intensity profile of the scattered radiation. This is purely a result of wave behavior and one of the fundamental properties of wave behavior, which is interference. In this particular example, d is the interplanar distance, lambda is the wavelength, theta is the angle of incidence, and n is the diffraction order. Now, essentially in a complicated scattering, n can be larger, but in this situation, I'm just comparing the first and the second layer of the crystal lattice. So in this case, n is going to be 1. So what Davisson and Germer did was they performed the same experiment corresponding to the X-ray diffraction via crystals, but using electrons, a phenomena of X-ray diffraction that we already know and established via the Bragg's diffraction formula to be something that rises due to interference. That experiment was reperformed for electrons by Davisson and Germer, and we will see that even for the case of electrons, we end up getting an intensity profile with maximas corresponding to this kind of a Bragg's diffraction formula, thereby proving the existence of matter waves as predicted by de Broglie. So let's talk about that. So what Davisson and Germer did was, they did a similar experiment where they had a nickel crystal, and on the nickel crystal they had an incident beam of electrons. These electrons were created by some sort of a heated filament, and those electrons were passed through a potential difference of 54 volt so that the electrons gain some kinetic energy, and they were scattered via some sort of a nickel crystal, and the scattered electrons were detected by a movable detector at different locations. So they varied or tweaked the energy of the electrons by varying the potential difference, and they also moved the detector at various angles to get an intensity profile. Now what they found was very surprising. For a certain kind of an energy of the electron, the intensity profile at different angles had a maxima or a peak at a certain angle. You see, for the given data here, for voltage difference to be 54 volt so that the electrons gain kinetic energy of 54 electron volt, it had a maximum intensity profile at an angle of 50 degrees. Now this is something that is very interesting because electrons are supposed to be particles. They are supposed to be, classically speaking, particles. Particles, we think, do not experience stuff like interference, right? When we talked about the X-ray diffraction, I talked about two wave fronts, and the bottom wave front experienced a path length difference, and because of the path length we had interference, right? But how can the same thing be true for electrons? Because electrons are not wave fronts. Electrons do not have path difference. Electrons are just particles, localized particles, or that is what we think, classically speaking. Unfortunately, the experiment is here to prove us wrong. The experiment here is to prove us that our thinking is not sufficient enough, and that what de Broglie suggested may have certain truth to it. So what happened was that there is a certain maxima that was created at a particular angle when the scattered electrons were detected. And this maxima can only be explained by the interference pattern of matter waves associated with the motion of electrons. The only way to explain the existence of a maxima or a peak in the scattered electrons after they get scattered by the nickel crystal can only be done by qualitatively giving in to the idea that the motion of the electrons is associated with some sort of a wave-like behavior, and this wave-like behavior is capable of interference, and this interference has a peak at a certain angle. That's what the Davisson and Germer experiment suggested. Let's look at the different kinds of values and the data associated with the experiment and see if we can come up with some mathematical correlation to it. All right. So in the Davisson and Germer experiment, they used nickel crystal. All right. The interplanar distance in a nickel crystal, d, is given by 0.91 nanometer. All right. And the electrons were passed through a potential difference of V is equal to 54 volt. So that we can say that theoretically speaking, the maximum kinetic energy of the electrons after having been passed through that kind of a potential difference is going to be 54 electron volt. And after studying the scattered electrons at different angles, they found that the maxima corresponded to this kind of an angle. So this angle is 50 degree. So let's calculate the angle theta with respect to this. So if I say that theta is basically the angle that the incident beam makes with the, surface or the plane surface of the crystal, then theta is basically equal to what? theta is essentially equal to, so if this is 50 degree and I draw, let's suppose, a perpendicular direction here, normal. So this comes out to be 50 degree minus 50 degree divided by 2. So theta is equal to 90 degree minus 50 upon 2. Alright. So this comes out to be 90 minus 25. So this comes out to be 65 degrees. In that situation, if we apply the Bragg's hypothesis or the Bragg's law corresponding to the maximas in the intensity profile of X-ray diffraction, in that situation the Bragg's law gives us that n lambda is equal to 2d sine theta. If I take the diffraction order to be 1, and then we get lambda is equal to 2 times 0.91 nanometer. So this is 10 to the power minus 9 meters times sine 65 degree. I think I have calculated the values here somewhere. So my calculation gives me a value of around 0.165 nanometer. So it means that this kind of a intensity profile where there is a maxima at this particular angle is possible for some sort of a radiation that has this kind of a wavelength. But we are not using radiation, right? We are not using waves, we are using electrons. So what to do about it? How can we correlate the wavelength of an electron? Wait a minute, the de Broglie hypothesis, let's check that. Let's check the de Broglie hypothesis and the wavelength predicted by the de Broglie hypothesis. Okay, so if we apply the de Broglie wavelength formula, what do we get? Let's check. Okay, so the de Broglie wavelength is essentially equal to h upon p. What is p? P is momentum. Now, what is the kinetic energy of the electrons in the experiment? The kinetic energy of the electrons was 54 electron volt, right? Now, what is kinetic energy equal to? Kinetic energy is essentially equal to p square upon 2m, where m is the mass of the particle, the electron, p is the momentum. Therefore, p is essentially equal to 2mke root over. So for a non-relativistic situation, the energies are not very high, by the way. For a non-relativistic situation, the de Broglie wavelength is actually equal to h upon root over twice m kinetic energy. So let's calculate this wavelength. Okay, so what is the value of the Planck's constant? 6.626 into 10 to the power minus 34 joules seconds, twice mass of a electron is 9.1 into 10 to the power minus 31 kgs. Kinetic energy is 54, electron volt is 1.6 into 10 to the power minus 19. Overall, half. I have calculated this value. Okay, let me check my calculations. My calculations gives me a value of around 0.167 nanometers. You see that this is actually almost equal to this particular value. The de Broglie wavelength that is predicted by the de Broglie hypothesis for an electron having an energy of 54 electron volt is exactly this. And this is the wavelength that is necessary to create an intensity profile that has a maxima at this particular angle, thereby providing an experimental proof that electrons are getting diffracted by the crystal lattice in the same way that traditional radiation gets diffracted by a crystal lattice because of the phenomena of interference between waves. So therefore, the Davisson and Germer experiment is a very important experiment because it provides irrefutable evidence that classical particles like electrons have wave behavior. They demonstrate wave-like nature, for example, diffraction and interference. And the hypothesis of de Broglie is not just some random hypothesis. It actually was proven to be true by this particular experiment. Therefore, this particular experiment is so very important. And what's even interesting is that this kind of a diffraction of electrons from some sort of a crystal material that contains peaks at certain angles is not just true for electrons, but they have also been performed for other particles like neutrons, whole atoms, molecules for suitable crystals. And we found, scientists have found, that these kinds of maximas do exist, just like a diffraction profile of an X-ray diffraction, thereby suggesting that this kind of a wave characteristic is not necessarily true just for an electron, but it is true for all particles, thereby creating one of the greatest mysteries in quantum mechanics, which is the mystery of wave-particle duality. You see, I started the video by saying that light has dual nature. Light behaves like particles and waves in certain experiments, but now we cannot ignore the fact that even electrons have dual nature. Electrons behave like particles traditionally, but in certain experiment, they behave like waves. And if the experiment says so, we have to accept it. There is no way to reject experimental evidence at all. So now we need to construct a theory to incorporate this idea that particles are traveling in such a manner that they have a wave-like property associated with it that are capable of interference and other kind of wave characteristics. Wow, that is interesting, isn't it? Well, that is all for today. But in my next video, I'm going to talk about something that is even more interesting, something that is related to this, an experiment that baffles the minds of scientists, physicists, philosophers, spiritual gurus, the experiment called the two-slit interference experiment of electrons. So till then, I'm Divyajyoti Das. This is For the Love of Physics. I'll see you next time. Take care. Bye-bye.